Okay, slide set number 3. And in this slide set, we are going to talk about your systems. So we saw a few things about signals in the previous slide set. And here we are going to talk about systems. And we'll start from very basics. And again, you can see that initial few slides talk about all the topics we are going to cover in this slide set, and also refer to the relevant sections that will be there. So let's talk about systems. So in systems, first of all, we saw there are different types of systems. Now, what a system does, it takes some input, does something to it, and gives you an output. So it transforms your input signal into an output signal. And out of the different types of systems, our linear systems are important for us, and time invariant systems are important for us, as I mentioned in my introductory lecture also. And I will keep referring to these two types of systems again and again, linear and time invariant systems. And together, we call both of them as LTI system. So LTI systems, it can be a continuous time system, it can be a discrete time system. And if you see that how we actually represent a system, here you can see if the input is x of t with parenthesis and output is y of t, and again t in parenthesis, we know that we are having a continuous time signal as an input and continuous time signal as an output. So that means we are talking about a continuous time system. And similarly, if we have x of n as an input and the output becomes y of n, we are talking about discrete time signals. That means the system that we are referring to is a discrete time. Otherwise, both of them are represented by a square box with arrow coming in and arrow going out. So this representation we covered in the introduction also. So some very basic things. The other thing we saw in the introduction lecture was that we can write an equation which gives us a relationship between input and output of a system. If it is a continuous time system, you would see that invariably we'll end up getting a differential or differentiation inside that equation. And that equation will be called differential equation. For mathematician, a differential equation is an equation which has got a differentiation in it. For engineers, a differential equation is an equation which defines a system, a continuous time system. And real systems has got input like this, Vs, and output like this, Vc. But typically, we don't write equations like this once we are dealing with the courses of signals and system or DSP. We just use the symbol Y for output. And if we see that this is some constant, whatever that value is, so we say that plus some constant time y of t is equal to some constant time x of t. Typically, we write an equation like this. So if you write an equation like this, it becomes more, you can say, nice to look at. And x denotes the input, y denotes the output. Now in real life, that x can be anything. It can be, let's say, source voltage, y can be anything, can be, let's say, voltage across a capacitor or current or whatever. But for us, signal system people and signal processing people, we say that we have an input x and output y. And again, looking at the equation, we can say a lot about a system. And by the time we finish DSP, you will become experts of just looking at differential equation and saying that, okay, this is a low pass filter, this is a high pass filter, this is an amplifier. You can just look at this equation and have a sense of what that system does. And that is something which at times impresses other guys like mathematician and all that, at how a person is able to see that as a system. Now, right now, that may seem a very far cry, but right now, if you just see something like this, yt is equal to 2 times xt. I hope anybody can just see it and say that, well, this is a system, it's an amplifier system. It just amplifies the input 2 times. Well, this thing, again, will be something you can boost for in front of elementary school guys or maybe high school guys. So you can just see that equation as a system and call it an amplifier system which amplifies 2 times. But again, as you just go along the signal system and DSP, you will get the expertise of looking at differential equations and say things about the type of system we are dealing with. Some things we can say directly, which mathematics can also say that what is the order? It's a first order differential or second order differential, and accordingly, it is a first order system or a second order system. Now, what that means in terms of system, that will become clear once you study DSP, that how a second order system differs from first order system, that types of thing. So in discrete time, if we try to write an equation which relates input and output, we invariably end up getting difference terms. And the equation that we get, we call that equation as a difference equation. So time systems are defined by a difference equation. A difference equation is an equation which gives us relationship between input and output of a system. Okay, I can see a question here. Yes. You see, LTI, we have to see that what are we talking about? It is a discrete time LTI or a continuous time LTI. If it is a continuous time LTI, it will have a differential. If it is any continuous time, it will have a differential. That's a separate thing. That what is a linear system? Now don't correlate that linear system with the linearity that you see in mathematics. That y is equal to 2x is a straight line. So that graph is a straight line, it's a linear equation. Y is equal to 2x square is curve, so it is not a linear system. So in that matter, what is y is equal to 2x plus 3? Linear, non-linear? Linear. But if you have a system, it will end up becoming non-linear. You see, that's an interesting thing because the property of linearity is kind of different once we talk about systems. Linearity property we'll see about 2 or 3 slides later. In that property, and we'll use that property to develop the first theories we'll use also. The linearity property for discrete time for this systems is that if we have 2 different inputs, then what type of output should we get? With x1 we get y1, with x2 we get y2. If we just give scaled sum of these 2 input as an input, a composite input, now the output that we get will be a scaled sum of the output that we should expect to get. Now, is that so? Does that happen? If that happens, then we say that we have a linear system. If that does not happen, we say we do not have a linear system. And again, once we talk about systems, we are going to see examples where seemingly the equation seems linear in nature, but practically you're not going to get that type of thing, and we're going to come to that in a few slides. Okay, so a discrete time system, once we try to write an equation which gives us a relationship between input and output, invariably you will end up getting a difference. This y of n minus 1, we can have n or y of n minus 1 or x of n minus 1 or 2 or whatever. So that type of equation will be a difference equation. And we already talked about this, that the equation that you're seeing here, this is sort of a bank balance where x is the monthly deposit that you're doing, the present input type of thing, and output is your y. And again, we can have a weird looking equation where you have, let's say, v's and all, v and f, these types of things, but typically we don't use that type of thing. So this v that you see here is output. So instead of just writing it as v of n, our convention will be that we will use y. And whenever multiple constants are there, we just lump them together and write it as one constant. That way the whole equation looks much nicer and much easier to deal with. Now we may have higher order systems also, for example, a discrete time second order system where we have a second order differential. So how do we describe the order? It is the highest order of differential that we have in differential equation, or highest order of difference that we have in difference equation. And here we can see that what type of response we get once we use those equations for systems. Now the left one, we see a continuous time system whose equation is given to us, and instead of x of t, we can give a particular input. Now this u of t minus 1, this is the input part. So we can give this input and try to see that what sort of output we can get. And these types of things we do in MATLAB using Simulink. In Simulink, we can just drop a box, and inside a box you can write a differential equation that dy by dt plus a times yt is equal to xt. And the xt that is coming in, for that xt you can just give different values to xt. Now xt can be a step signal u of t, it can be a delayed step like you see here u of t minus 1. If you see, u of t is a signal which starts at 0, and then becomes 1 at 0 and then remains 1 throughout. That is your u of t. So what should be u of t minus 1? It has to be a shifted signal, and will be a shift right. If you see here, instead of this yellow line starting from 0, it is starting from t equal to 1 and then remaining 1 throughout. So this is your input. Right? And if you give this input, we can just see what sort of output we get. What will be y of t? So this is your x of t, and this is your y of t. This is your x of t. This is your y of t. So we can give different x of t and just see the plot of how y of t will look like. So these types of things we can do in MATLAB using Simulink. Similarly, we can use difference equation and see that what happens once we use difference equation. So here again, the equation that you see is a difference equation, and this is basically your input. So instead of giving it x of n, we can just first of all drop a box where we can just write an equation inside that box. Okay, this is the system and it should obey this equation, and input is x of n, output is y of n. And for x of n, we can give different values. So we can give shifted version of step signal or scaled shifted version of step signal. Here you can see it is having a scaling factor of k. So that k can be 1, 2, 3, 4, whatever value you want to give it. And u of n minus 1 is basically just your step signal shifted right by 1 time unit. So we can give that input and see what output is. So in this particular case, the green lines that you see are the input, and the red lines you see are the output y. So these types of things we can just do in MATLAB. So the take home thing from here is that we have a continuous time system, discrete time system, continuous time described by differential equation, discrete time defined by difference equation, and we can use MATLAB to just write an equation and then give different inputs or different values to x of n or x of t and see output y of t or y of n. We can do that. So MATLAB can deal with both types of things, discrete and continuous both. And these are the type of things you may practice in your lab. Okay, now coming to that question about linearity. Now this is the interesting thing. So what is linearity? It is one of the most important properties that we have in system. And two important properties that we are interested in are linearity and time invariance, because you will see that all our theories that we are going to study throughout our engineering and later on in life also are based on that assumption that your system is linear and time invariant. Now what happens if your system is not linear? What happens if your system is not time invariant? Then these theories fail. Then different theories have to be used, or these theories have to be modified and used. For example, a nonlinear system, we can still use these theories of linearity, but we can just apply it for small patches, in small, assuming that system is linear for a small duration. So again, those techniques are covered in higher level mathematics, higher level masters and PhD level courses. In undergrad and even in basic masters, you're not going to deal with nonlinear system or time variant systems. Those are complex systems, and complex theories are required for that. Okay, people sitting here, please write your attendance on a piece of paper. For those online, I can always see who are online and I can just mark it accordingly. Any questions? So we are going to cover this part next time, because this is serious part, linearity and properties. We'll cover that next time. So online guys, any question? So if there are no questions, then this is all from my side. So last time we were covering this slide set number 3, and let's continue with that. And what we are going to cover here, we have already covered some basics earlier also in the introduction part. So let's start from the very first type of system, that is linear system. As we know that linear system play a crucial role in most areas. And I think I have been talking about it that for the theory part, for developing the theory, for developing all the logics and different types of, you can say, methodology, we assume that all systems are linear. And we also and we also assume that all systems are time invariant. And together, these two properties of linearity and time invariance are lumped together, and we call that type of system as linear and time invariant system. So you will see that how all the theories are developed assuming that our systems are linear and time invariant. How do we represent a system? It is mentioned here. So we have this sort of a square box, and the input, if it is x of t and output is y of t, with this curly sort of a bracket. So that means we are talking about a continuous time. For discrete time, the same type of a box, and but the input will be x of n with this square brackets and output y of n. This is how we represent a system. We saw it last time also. And how a system can be represented mathematically, we talked about that also. For continuous time system, we end up getting a differential equation. This was with the example that we saw. Although we don't actually use this VC or VS, we tend to go with the terminology of X for the input and Y for the output. So typically we just take input as X of t and output as Y of t. So instead of X of t and Y of t, if we have something else like VS or VC, we will just replace it with Y here. This is supposed to be the output, and X here. That makes the things more simple for us. So if we have a continuous time system, then if we want to write an equation which gives us the relation between input and output of a system, we end up getting a equation which has a differential in it. It will be a differential equation. And I mentioned that mathematicians call this a differential equation, and engineers tend to see that equation as a system which gives us relationship between input and output. Similarly, if you have a discrete time system, then the equation which will give you the relation between input and output would be called the difference equation, because you will see that once we try to write the relationship mathematically, we end up getting a difference equation where you have a differences like this. And we saw this example also last time, that this was actually equation for monthly bank balance. That was the example that we did. And again, we can have multiple different types of equation that can result for different types of systems. For example, this is a second order system because the differential is second order. So we can have multiple different types of equations for systems. If it is a continuous time system, you will end up getting a differential equation. If it is a discrete time system, you will end up getting a difference equation. And the orders of the system will be determined by the highest order differential, whether of y, whether of x, whatever is the highest order of differential, that will be the order of the system. Similarly, for discrete time, it will be the highest difference, whether with y or with x. So the highest difference will determine the order of your difference equation. So more or less what we covered last time, just sort of a review of that. Next, we saw that we can use Simulink, and in the lab you will be covering MATLAB and Simulink, and you will see that in Simulink how we can actually write an equation, and then in that equation we can give different inputs, x of t equal to u of t minus 1 or u of t, and see that how the output would be. In this given example, Simulink was used for this equation, and the input given x of t was u of t minus 1. Now u of t, we have seen u of t was actually a step signal which became 1 at t equal to 0 and remained 1 throughout. The shifted version, one shift right or shifted right by 1 second, would be u of t minus 1. This is signal which is shifted by 1 unit. You can see here that this starts from 1. Instead of starting from 0, it is starting from 1. So this is u of t minus 1. This was the input given, and for this type of system, for different values of a, you would see that the output that you get, that yt, would become something like that. But these are the examples that will be covered in the lab. You can just drag and drop different types of, you can say, boxes and equations and then see that what output would be if you give different inputs. That is what MATLAB and Simulink will be doing for you. You can just practice it in your labs. Similarly, we can just take a different discrete time system with a particular difference equation and give different types of inputs. Here the input given, here the x of n was some multiple of u of n minus 1. We know that u of n is basically unit step, all one starting from n equal to 0 going all the way to infinity and shifted by 1 unit to the right. So it starts from 1 instead of starting from 0. So this green is basically your input and it is going on and on and on all the way to infinity. This was basically your u of n minus 1 and some scaling factor here, k is equal to 1. So we can just keep changing value and the output is shown in the red, that is your y of n. So this is just to show you the type of examples that can be practiced in MATLAB and Simulink. Okay, let's talk about the property that we have seen earlier, the property of linearity. What is a linear system? We have already covered it in the introduction part, that what is a linear system. And we saw different explanations for a linear system. And basically what it meant was that if you have a system in which if you give, let's say, x1 as an input and output was y1, and once we gave x2 as an input and output was y2, then for the same system, if we give sum of these inputs together, we just sum these inputs together and give it as an input, the output that we should get should also be the sum of their individual outputs. If that happens, then we say we have a linear system. And actually it has two parts. This property where we can just add two signals up and find out the output is addition of their individual outputs. That is the additive part of linear system. Similarly, we have a scaling part. In scaling part, what it means is if x1 was giving you y1, then a times x1, a scaled version of x1, would give you a times y1. So this is basically the scaling part. So the property of linearity has basically two parts. One part is the additive part, the other part is scaling part, and these two combined actually give us the linearity property. Scaled version of x1 added to scaled version of x2. If given as an input, the output would be scaled version of their y1 and scaled version of y2. So like this. So this is basically mathematical representation of your linear system or property of linearity. So we covered this earlier also, the linearity property. So linearity property has basically two parts. One, the additive property, the other scaling property. Now, if we just look at the equation, now mathematicians look at that equation and think in terms of graph, think in terms of graphical representation of that equation. So here, if we see this equation, we know that it is going to give us a straight line. It is going to give us a straight line of this type, passing through the origin and just going up like this. So this is a straight line. Now, typically, what mistake engineers do is they tend to think like mathematician and see the equation. And if they see an equation of a straight line, they think that it will be a linear system. Now, this is not always true. In this case, this is true. It will be a linear system. But if you see the second equation, this is also equation of a straight line. But this equation of a straight line is not representing a linear system. So why it is not representing a linear system? Because it will not obey the linearity property. These properties that we have seen, additive and scaling together combined, this second system will not obey it. Other equations which are non-linear by the very design, they obviously, if you just see, it will not obey your linearity property. And mathematicians also know that it is going to give you not a straight line, but sort of a curve. But this is something which at times confuses people. So let's see that how we can say that the second one was also a non-linear system. So if we have, let's say, a system which is defined by the equation that you saw, if we give, let's say, x1t as an input, output was, let's say, y1t. And if we give, let's say, x2 as an input, and output was, let's say, y2t. Then, as per our definition, the additive property x1t plus x2t given as an input should give us, if this was, let's say, x of t, the input part, if this is given as an input, the output should be just the sum of these two, y1t plus y2t. We should be getting this type of a thing, yt should be this. Now, if we just see the second equation, which was yt is equal to 3 times x of t plus any constant, let's say 2. Then x1t would be equal to your 3 times x1t plus 2, and y2t would be equal to 3 times x2t plus 2, right? So if we just add them together, so yt, if we just give that sum as an input, the output yt would be, we can just add these two together. I can just take 3 common, and here I should get x1t plus x2t plus 2 plus 2, it will make it plus 4. Now this x1t plus x2t was xt, and if we just plug in the value here, you will see that the equation that we get would not be the original equation that we started with. This is not right. This is not right. It should have been 2. So that means the additive part is not obeyed. In comparison, if this constant part was not there, then adding these two would give you the same equation back. If you don't have this additive part, if this part was not there, if this part was not there, then it will obey your linearity property. Then your linearity property would be obeyed. So just looking at the equation at times can be confusing. Only if we just check it, then we will find out whether we have a linear system or not. So from equation can be an equation of a straight line, but if we just check it, that is going to tell us whether we have got the same thing or not. So this zero bias and all that, this we are not going to cover. So why this linearity is so important? The linearity is important because you will see here, if we just see the superposition property. Now what is superposition? Now suppose that we have a signal x of n, which comprises of a linear sum of other basis or simple signals. Then we can write x of n as, let's say, a1x1 plus a2x2 plus a3x3. We can just write it like that. So this is basically a property where we have just added basic or simple signals together and come up with a more complex signal, x of n. Or in other words, breaking the complex signals into simple signals. And these simple signals, once we add them together by, we can just say superposition of all these signals together. Superposition is basically addition. So addition or superposition of these signals give us a more complex signal. Then the output, if you want to find out output for complex signals, we can easily find that, because all we need to know is that how the system responds to more simple signals. Let's say if simple signal is x1, we know that output of x1 is, let's say, y1, output of x2 is, let's say, y2, and like that it goes on. If you know this response of system for simple signals, then we can just add simple signals together to come up with more complex signals, and we can find out response for more complex signals. So this is basically the reason that we are interested in a linear type of systems. Now this will be true only if your system is a linear system and obeys the property of linearity, the additive property, although the scaling part also is included here. So if system obeys the property of linearity, then we can do this. So what we can do is, we need to first of all know the response of system for very simple or basic or basis signal. Now this term basis, what does this basis signal mean? Does anybody have any idea what basis signal mean or what basis itself means? Any idea? Anybody? So this term basis, this is very interesting. Now, I'm sure many of you are familiar with Lego blocks. Is that right? Have you ever heard of Lego blocks? Any volunteer? Anybody who knows what's a Lego block? Kids play with this. I'm sure as a young person you may have been playing with these Lego blocks. What's a Lego block? Volunteer, what's a Lego block? Do we have a volunteer answering this? What is a Lego block? Okay, so nobody wants to answer. I hope I'm audible to you guys. So any volunteer who can tell me what's a Lego block? Exactly. The small blocks which we can just combine together and make complex shapes. So just like we have Lego blocks can be used as building blocks. We can just use small of these blocks and build more complex shapes or figures or different things. So this basis is also that building block. So basis signals are again simple signals which can be used as basis, as building blocks. So just like we have Lego blocks, the same terminology can be thought of for the basis signals. So basis signals are supposed to be those signals which can be used as a basis, as building blocks. They are simple signals which can be used as building blocks or can be used to make more complex signals. So the basic idea here is that if we understand how the system responds to your simple signals, how it gives you output for simple signals, then we can work out or find out that how the system will respond to complex signals. Now these simple signals, our interest is that we should know that how it responds to simple basis or building block signals. If we can find that out, then we can find out how the system is going to respond for more complex signals, because what we can do is whatever complex signals we want to find the response of, we just break that complex signals up into simple signals, just like you see right here. We just break it up into simple signals, and we can just think of that complex signals as scaled sum of some basis or some simple signals. And then we know response for basic or basis signals. We can then just see that what is the total signal here, and then accordingly find out the total response, because it will be just first of all individual responses and then add all of them together and you get your final output right here. So that's the basic idea. That's the basic idea behind all this, that we should know that how the system responds to simple signals, and then we can just break the complex signals up into simple signals and find out the response for individual simple signals, and then we can just find out response for the total complex signals. Now this is the superposition property that we see here, that we can consider your complex signals as being made up of simple signals superimposed, or superposition of simple signals giving us more complex signals. So this superposition property, which we are seeing right here, we break up the complex signals into simple signals, and this superposition of simple signals is giving us the complex ones, and we find out response for simple signals, and then we find out the response for more complex signals summed together. Now this is true for both continuous time and both discrete time type of systems. So continuous time system also can be looked at in this way, and discrete time systems can also be looked at in this way. And this actually will give us the concept or give us the theory of convolution. And this is important for understanding the convolution theory that we will see in the next lecture. maybe in this lecture at the end or maybe in the next lecture, we are going to see that how this simple theory or simple concept actually gives us the convolution theory. Okay, that was regarding the linearity. The other property which is important for us is that of time invariance. We covered that property of time invariance earlier also, and time invariance we saw is basically a property which actually tells us that the system response remains the same no matter at what time the input is given. Whether you give it at t equal to 0, whether you give it at shifted version at t equal to t naught, whatever time you give a particular signal, the output that you get from your system remains the same. It does not change. If the time of input gets changed, the output will not get changed. So what it actually means is that if you have a, let's say, system which is taking, let's say, x of t as an input and giving you y of t as an output, and if you give, let's say, x1t as an input and output was, let's say, y1t, then shifted version of x1t, if you give, let's say, x1t minus t naught, x of 1 shifted by t1, the output also gets shifted by the same amount. The shape will not change, the response will not change, but shifting the input will shift the output also, but response remains the same. This is time invariance. So for example, if y of t, the output that you get is basically sine of the input, sine of x of t. If this is the differential equation for defining your system, then if you just give an input x1 t minus t naught, shifted version of the same input is given, the output would be sine of x1 t minus t naught, shifted version of your output. So this is what this means, and this is true for your continuous time and discrete time both. So some new properties also are mentioned here, maybe one or two additional things we are going to cover here. One property is the property of memory. So what is a memory system and what is a memoryless system? So a memoryless system is a system whose output depends on input at present time only. The output does not depend on any past or future input or output. Its output depends only on the present input. So example is shown right here. Output y of n is basically 2 times x of n plus xn square, the whole thing squared. So this whole mathematical formulation actually requires your present input only. It does not require any x of n minus 1, n minus 2, any previous input or any previous output. Now that's a separate story, whether it's a linear system or not, that's a separate story. But this is a memoryless system. Another simple example of memoryless system would be a amplifier system. Let's say this is 2 times x of t. So here, if you see, the output just depends on input at present time x of t. It does not depend on any past input or output. So we don't need to store any previous values to compute your present value. So this is a memoryless system. Now what is a memory system then? It will be opposite. The output will depend on some past input or output. So that is a memory system. For example, here you see the output is basically the previous input is the output. So to compute the present output, we need to have a storage, a memory of previous input. That actually is a memory system. This is a simple delay system. What this thing is doing is just delaying the input by 1 and giving you that as an output. Simple delay. So this is a memory system. This is a memoryless system. Now we can give examples of any discrete time or continuous time memory or memoryless system. Now one of the most common memory system that you computer engineers especially come across is an accumulator system. Now it's an accumulator system. So if you have any system which just accumulates or keeps adding on all the inputs till present time, that will be an accumulator system. So for an accumulator system, the output y of n is actually the accumulation of or sum of all inputs till that present time. That's an accumulator system, a very common system that you computer engineers especially will come across a lot. So if output is sum of all the inputs till this time, then this is a accumulator system, and you will deal with this accumulator system in multiple circuitry, in multiple systems. So we can just write it in summation shape also. This is basically x of n minus k, where k is equal to 0 all the way to infinity. This is a accumulator system. So if you just open it up, you end up getting the top line right there. So this is a accumulator system, right? Now the interesting thing about accumulator system, if we just open this up, or let's say we want to find out y of n minus 1 for an accumulator system, that would be x of n minus 1 plus x of n minus 2 all the way to infinity, and this will be just sum of k equal to 1 to infinity x of n minus k. So this will be your y of n minus 1, output of accumulator system. That was one previous output. Now using this equation, I will just call this as equation 1. Sorry, this is equation 1, this is equation 2, and if we just see this equation 2, we just open this summation up, we can just take the last term out and write it as y of n is equal to, from the summation we just take the last term out, it will be x of n minus 0, or simple x of n, plus sum of k equal to 1 to infinity x of n minus k. We have just taken the last term out, and this whole thing is what we see right here, the previous output. So we can write this y of n as x of n plus y of n minus 1. So this is also the same accumulator system. So this equation 3 we can call this. So equation 1, 2 and 3, all of them are one and the same thing. The beauty here is that if you want to build an accumulator system, one way is that we store all the inputs and then sum them up and get the output. So whatever input is coming, we just keep storing it. But we need a very large storage for this. It will be a memory system, but we need almost infinite memory to build this accumulator system. A much simpler way would be just keep the previous output, just store the previous output, and whatever new input comes in, add it to the previous output and you get your present output. So a much simpler way of building an accumulator system. Now this type of simplification later on, once you become computer engineers, you will be doing this type of simplification for building different types of systems and circuits a lot. So this is just showing you that we can, just by a bit of rearrangement, simplify systems a lot. So this is an accumulator system, which is a memory system. So the basic thing that we wanted to cover here was that what is a memoryless system and what is a memory system. So we saw that this is a memory system and this is a memoryless system. This is a memoryless system. And the same thing that you saw for accumulator, we saw that memory systems at times can be simplified by just doing a bit of mathematics. Okay. The other property that you see here, we have already covered this earlier also. It is basically the causality property. Now, what are causal systems? We covered that also in the introduction part. We covered actually three systems: causal, time invariant and linear system. So we covered causal systems also. So what are causal systems? Those are systems whose output depends on inputs or outputs till present time only. It does not, the output does not depend on any future input or output. So this is what is shown right here, that your output y of n will depend on the present and previous inputs. Here we are talking about inputs only, but even the previous outputs also are good enough. That will still keep the thing causal. We don't need any, or we don't want any n plus term in your difference equation. So if to compute your output y of n, we don't require any future term, any n plus 1, 2, 3, whatever term. That means we have a causal system. We just require previous inputs or outputs. So if you see your this previous accumulator system, y of n is equal to this. This is a causal system because we require just present and previous inputs or outputs. We don't require any future terms. And if your opposite of causal is anti-causal, if your output depends on future terms only, here we are showing future outputs, x of n plus 1, x of n plus 2, then it would be a anti-causal or opposite of causal, anti-causal system. And we mentioned this also, that almost all, if not all, then almost all physical systems are causal, because if you patch up a circuitry, it cannot really predict what future current or voltage would be. It will just give you a response based on present inputs or previous inputs. So that is the causality property and causal systems. We have covered it earlier. I'm just talking about it again here. Another very important property, which is again a new property that we are talking about here, is the property of stability. Now this is again a very, very important property of a system. Now simply put, stable, there are basically two type of explanation given right here, first and second. First one you will have a hard time digesting. Second one is more, you can say, understandable. Let's talk about the first one. Informally, a stable system is one in which small input signals lead to the responses or outputs that do not diverge. Or if you go towards the second explanation, it is a system is thought of as being stable if an input signal, it will be stable if for an input signal which is bounded, we get output which is also bounded. Then we say we have a stable system. If an input signal is bounded, then output signal must also be bounded if system is stable. So mathematically put, it is just saying that for all input x such that the magnitude of x is less than some constant, so it has some upper bound, so it is not infinite. So if input is such that it is bounded or it is finite value, less than some finite value, then the output magnitude or value will also be finite, will also be less than some finite value v. So this is mathematically saying the same thing, and we tend to write it as BIBO. A system is stable if for bounded input it gives bounded output. Then we say that we have a stable system, bounded input giving bounded output. Now, how do we actually check whether a system is stable or not? For that, one way is we can just find out its output for all input signals, for all finite or bounded or known signals. We just see what the output is. If for all input signals, which are, let's say, not infinite, for all finite input signals, the output is also finite, then we say the system is stable. Now, obviously, this is a theoretical thing. We can't really practically do it. We cannot give all types of inputs and keep seeing all types of outputs. A much better way to check about this thing is if we can somehow come up with any counter example. If I come up with any counter example, that means if you can find out that for any particular signal the output becomes unstable or infinite, then we will say that your system is unstable. So if we see the example of this discrete time system, which was a bank account system, which we saw earlier, you will see that this will be a unstable system. Although I can just look at it and tell you that it's unstable. With time, once we go through it in detail, you will see that how we can simply check and then just by looking at it, how we can say that the system is stable or not. So if we see this, how I was able to say that this is unstable was, we see that if we keep giving input, the output keeps increasing. So the output tends to grow without any bound, and after this is because of that multiplier part, 1.01 multiplier. So output gets always enhanced whenever we give any input to it. And this actually tends to make the system unstable, because with time it will tend to diverge and go towards infinity. Now, in electrical circuits also, the constant part is important. This RC part is important. And if we just see the combination, we will be able to just judge whether we have a stable system or not. Typically, all practical electrical circuits tend to dissipate energy and they are stable. But how do we check whether a system is stable or unstable? This is what we are going to see. It is a very simple method by which we can check whether a system is unstable or stable. So theoretically, what stability means is a system would be stable if for a given input the output remains finite. If for given input, whether we have a discrete time or a continuous time system, if for a given input output tends to become infinity, then we say we have an unstable system. Now this unstable system, what does it mean practically or reality? In reality, can we have an unstable system in reality? That is something that is very interesting, especially the electrical circuits. If we purely see the theory part, that means that for a given input, if output becomes infinite, then we have unstable system. But practically, that doesn't really happen, especially for electrical circuits. For example, the circuit that we saw earlier, that was the output being, let's say, voltage across a capacitor. Now, if for any given input, the voltage across a capacitor tends to become infinity, then you would have solved the energy problem of the voltage. So, but that actually doesn't really happen. Theoretically, it tends to go towards infinity, but practically, it just saturates. It just maxes out. So, this is something that we are going to cover in detail in next about 2 weeks later, maybe next week. So, we are going to cover that in detail. Okay, we are going to cover this stability in detail in next lecture. Any questions so far?